lecture today. Today it's my great pleasure to introduce today's speaker, Professor Tony Waas from University of Washington. Professor Waas is currently the Boeing Agvet Professor and Chair of the Department of Aeronautics and Astronautics at the University of Washington. He earned his PhD in aeronautics from Caltech, and he served on a faculty at the University of Michigan for about 26 years. He has made many contributions in the field of mechanics of composite structures, for which he received many awards. I just name a few. He received the 2016 AIAA ASME SDM Award, 2017 AIAA ASC James Stanners Award, and he was recently elected to the Washington State Academy of Sciences. So without further ado, let's welcome Professor Waas.
All right, well, good morning, everyone, and thank you very much for coming to this seminar. Thanks, Jialing and Bob, for having me here for this lecture. Before I start, I want to thank my students in the Composite Structures Lab, first at Michigan and then at Washington, and postdocs and colleagues. Been very fortunate to have a great bunch of colleagues at Michigan and also now at Washington. So in my talk, I'm going to outline some of the work that we did on 3D textile composites. These are widely used and are continuously being refined and used more and more in the aerospace industry as well as in other infrastructure applications. I will describe some tests that we did to understand how these materials fail progressively, and how we can tune the microstructure of the material to sort of design the outcome of what we want, how we want the structure to behave. In a sense, materials design. And then I'll show a model that we developed that has a lot of elements of mechanics and issues of mesh objectivity, etc., that are required in order to construct a good mechanics model. Then I'll offer some concluding remarks and finish up. So these materials are finding many applications that are dictated by weight, lightweight in the naval industry, aerospace industry. This particular application, these types of composites that I'm talking about are of interest to the Army, where they are trying to apply these to ground vehicles, armored vehicles, replacing tankers, other equipment made with heavy steels, because it's a logistics problem. If you want to fly these vehicles overseas, a 747 can carry only so much because of weight. But if you reduce the weight drastically, the logistics issue is solved, and in the process you can design much better vehicles tailored to requirements. These materials have architecture. What I mean by that is that you have length scales varying from meters, which are structural level, all the way down to microns, which are at the microstructure level. So here's just a little snapshot of braided composites that they're built. They're also manufactured in an automated manner, robotically. So that's another advantage, right? So the manufacturing process is more controlled in terms of getting a product that has more precision in the microstructure, the control of it. So you have yarns that are interwoven in some manner, which you can control depending on the machine you use. And then they are infused with resin under a vacuum, and you get a product which is a structure then. It has the ability to also be manufactured of net shapes. So the shapes that I showed you in the earlier pictures are facilitated by the production of the material as well. So there's some advantages, no connections, etc. And it's an old technology, right? Weaving is one of the oldest technologies, right? Our jackets, Nike shoes, they're all woven and they're mechanized. So a bit of imagination and creativity, if you can make a shoe that's size 10, you can make a shoe that's size 100. And so you start thinking of scaling things up, and you can make very large structures quickly, right? And so as mechanicians, we have now to come up with frameworks to analyze the structure to be able to predict how such a structure would behave. So it's a weaving process that I'm showing here as a illustration. And the yarns can be different. You can have glass, Kevlar, carbon. Some are now thinking about ceramics like silicon carbides, etc. as well. And the architecture is controllable. Now, in this particular type of materials that I'm talking about, there are yarns, what I would call in plane, if it's a panel. And then there are yarns that are going out of plane. That's the zigzag, the somewhat crushed sinusoidal type wave that's going through, binding all the in-plane yarns together. So if you start breaking this up, you will see different length scales all the way down to the micron scale. You see the fibers and the polymer in between. Now, material scientists are interested in manipulating the microstructure even at a decreasing scale. For example, the interface between the fiber and the matrix can also be manipulated. And so there's a lot of work going on in material sciences and mechanics where we look at decreasing length scales. But the disadvantage there is that the computational cost increases. You have very good fidelity, but your cost increases. So there's a balance. You have to understand which scale to start your calculation and which effect that you want to measure. So there's a trade-off. But I think as time goes on, we will see a day where we'll incorporate more and more scales in a single analysis as computing power and as computing architectures become better. All right, so this is a depiction of the materials we looked at, and this, as I said, was for the Army Research Lab. And these are the architectures we looked at. They're very close to the real thing. You'll see in a minute when I show you actual pictures. So the particular layer, we changed the number of carbon layers, the number of glass layers, and the number of fibers that are going through the thickness. And you can see two patterns. You may see in the literature something called a 2.5D composite, not a 3D. And that what it means is that the binder is not going through all the layers if it's a very thick structure. The binder is zigzagging, and there's two sets of binders going through. And you'll see in a minute that it actually has an impact on what you predict for the performance. We take measurements of the microstructure either through scanning electron microscopy like this, randomly chosen from different parts of the panel, or more recently, there is technology where you can take a micro CT scan of a fairly large structure, and you can convert that to a numerical model. There's companies and software that's doing that. In the medical field is quite advanced in that, where they take, for example, an X-ray of a bone, and they convert that into a numerical model that mechanicians can manipulate and analyze. So that field is evolving as we speak, and the advantages are many, especially for people like us, mechanics of materials people. We really want to get a handle on what's the internal microstructure of the material we are looking at. So let me describe a little bit of the flexural tests. Very standard. Civil engineering audience, mechanics audience knows this. These are standard 3-point, 4-point bend tests, and the diagnostics are DIC, digital image correlation, and we used a configuration that we can also look at under low strain rates. If you want to go to very high strain rates, we've done that as well using split Hopkinson bars, but we can also look at it fairly in the middle range by using a drop tower. So the configuration is amenable to looking at both static as well as low to high strain rates. Now, strain rate response, right, an event at the macroscopic level can have high loading rates, but locally the material may not actually experience the same rates in terms of strain. So you can have low strain, high rate, or high loading where you subject the structure to very high strains, but the rates are still low. So you have to look at the time scales of the events that you're trying to study. Now, the architectures that we tested, we collected a lot of data. We also have another configuration that is also used by the United States Army. Albany is a company that manufactures these for them. Those are undulating structures I'm showing on the right-hand side, where there's no 3D binder layer. The layers themselves are interlocked and they're binding. So it's still a 3D composite, but there's no third layer that's holding all the other yarns together. Now, this picture shows why the microstructure matters and why you can change your microstructure to affect the behavior you want. So very roughly speaking, you can think of the area under the curve as kind of the energy that's dissipated in an event, right? So you can see that different configurations produce vastly different responses. That's number one. Number two, you can tailor the length of what I would call a plateau load. So for applications, let's say in a crash, in a car, frontal end of a car, say you want a car hitting a wall, right? What you would want is that plateau region to last for a longer time so that the deceleration pulse does not hit the driver as quickly as possible. Now, let's say the front end of the car was made of diamond, right? As soon as it hits it, the waves transmit very quickly to the driver, and the driver will be ejected out of the windshield. So the point I'm trying to make is that you can actually tailor the structural performance of the front end to impact what the the head acceleration levels of the occupant is in a vehicle. That you can't do very well with, let's say, a monolithic material unless you have lots of geometrical control, because we know that geometry can also help us. But if you have material control, material microstructure control, you have that additional advantage that you can design the geometry of the larger structure, but tailor the microstructure as well. So now your design space is much more open, right? And therefore, you can actually pretty much dial in exactly how you want that vehicle to collapse. So this is very attractive for civil engineers as well when you do, say, bridges, collapsing, earthquake-resistant structures, for example, right? You have your inputs, you have your outputs, you're designing the middle part, which is your structure, but now you're taking advantage of the fact that your microstructure is also tailorable, right? So that's, in a way, sort of a paradise for people doing mechanics of materials and design and the like. So you can affect the behavior quite widely by these materials. Now, this is the movie we wanted to check. I had a little computer snafu when I came here. Let's see. Okay, let's see. It should run. Nope, it didn't. I'll give it one more try and I'll move on if it doesn't work. No, it's not working. Okay, so what I wanted to show you here was, let's see. All right, so sorry about that. What I wanted to show you was how the progression of failure develops as we 3-point bend the structure. And then I want to show you one without the speckled images, how it fails. I can describe it. It linearly responds, and the tensile side of the specimen starts to show cracking. But the cracks are not allowed to grow. So the cracks occur, producing some ductility, right? And then that final collapse is when the top carbon layers fail in kinking. And in the morning, I went to the rock mechanics lab, and I was delighted to see kinking is a version of shear banding in rocks, right? It's very similar. The mechanics is very similar. And in fiber composites, the important material property that controls this is the nonlinear constitutive model for the matrix material, not the fibers, right? One would think it's the fibers, but it's not the fibers. It's the matrix that controls it. So that's what then leads to that collapse. And then what happens is that it picks up load again because across the band, loads are still transferred. And so the top layer starts to do what I call multiple kink banding. So you're making use of the material more, right? You want the material to crack, but you don't want it to localize and suddenly rip into two pieces. You want that kink band to absorb a lot of energy, which it does, but then you want to delay complete collapse by getting it to kink more and more. So progressive kinking. So that's what controls that plateau. It keeps going forever, adding this ductility. Now, these are termed quasi-brittle materials, right? One is a fairly ductile material, the polymer. The other is a very brittle material. But you combine the two and you can come up with a material that behaves almost like a steel, like a metal. Yet it's light, very light, but 10 times less dense. So your specific strength, your specific stiffness is very, very high. It's very attractive. Light, but behaves like a metal, right? So let's see. Okay. Are we stuck or click out of it? All right. Do you know whether I am? Okay. Ah, there you are. All right. That's why he's the chair. All right. So here's another picture showing what I just said in a much broader, more, shall we say, a ductile behavior that you get from these brittle materials. By designing the microstructure, you see the failure starting on the top there, compression. That's because the carbon's on the outside and it propagates. This is a thick structure. Now, after point E, when you unload it, there's a lot of elastic spring back. Unlike a steel, if a steel structure is bent into this level, when you unload, it stays. You disrupted the geometry. Here, it's damaging. It's not permanent set, so it comes back. Now, it will not come back exactly because the cracks, the path of reversibility is not exactly satisfied. So crack opens up. When it comes back, it doesn't come back exactly the same way. That's why there is a little bit of residual damage left in the structure.
What's the scale? We have millimeters on the displacement.
Right.
In terms of percent.
This is about an inch thick structure. It's 1 inch thick panel. Yeah. Sorry about that. Yeah, should have put that. So here are those DIC pictures that we can analyze. You can see that the micro cracking in the matrix sets up at the bottom, and then finally, when it completely collapses at the top, you get those kink bands, and they progress while it's propagating. Now, this is a huge challenge for modeling, right? So all glory to one of my students that did this work, Dianyun Zhang. She's now a professor at University of Connecticut in mechanical engineering. So here I'm showing also how the toes, the fiber toes fail while so this works. You can see that it kinks there, and then if I start looking at it closer and closer, you'll see the progressive kinking that you see in those bands, that the shear bands that form in those layers, and the bands keep transferring load, and you get another shear band, and you get another shear band, or we call it a kink band, and it continues to grow. But that's good. It's contained, and therefore it's dissipating energy, but in a localized zone. And so final collapse occurs when the bottom toes in the structure fail in tension, tensile failure in the carbon toes. The kink banding There's some nice pictures in Professor Labuse's lab that I just toured in the rock mechanics lab. Very similar. The fibers are straight, and then what happens is that you get a limit load instability, snap back, you get in the structural plane, but in the real structure, the unstable equilibrium path is lost. You get a vertical load drop, and you get a kink band, which is a band that's at a particular angle, right? And then at the corners of the band, the fibers actually break because the bending stress, the tensile stress on the fiber on the lateral side is much more, so it snaps. So it also, but that energy is small compared to the energy that is dissipated in the shear in the polymer matrix. We also did some drop weight tests using a drop tower under the same configuration, double rollers to make it not rebound. Now, these are some of these results are filtered. The high frequency noise is taken off. You can see that as a function of the loading, you see different behavior. But if the carbon layers are on top, you get a lot of ductility, so-called ductility. But if the glass is on top, you get abrupt failure. So microstructure will influence how your structure is going to behave, and they may not be the same when you change your loading rate. More here, and I'm going to explain the oscillations in a minute when we look at the movies again, if I hope they play. There's a movie here. Let's see. I have to click this. It's playing. Good. So you'll see that these oscillations, after you take out the high frequency noise, is failure. There it is. You can see the failure occurring. And each failure point is an abrupt drop because of the localized failure, but the load picks up. And so this is not noise. This is actually a deterministic event which is controlled by the microstructure and the fact that it's contained. And you can see the glass. So if you design it well, you can make this progressive failure event last even longer, right? That ability exists for you to control what you do with the material, right? So materials design, controlling structural response. And I'm glad this worked because it's a great, we've got more movies like this. So if you look at the other one, where we put, this is an unsymmetric laminate. If you put the glass on top, now you'll see what happens. It starts, by the way, when this roller is lifted up, there's a lot of elastic energy in the rest of the structure that will lift it back up. It completely disrupts itself because the carbon, the tensile strength, once the bottom tensile layers rupture, it just collapses and you get. So why is this important to the Army? Because the armored vehicle walls are not symmetric. What's on the outside has some ceramic layers, and you can have external threats. What's on the inside is where the occupants are. So you can tailor your microstructure depending on which application you want to use it for. So the events are like this, right? I just captured schematically what happens in these materials. You get a linear sort of response governed by the geometry and the stiffness. Then you get this matrix cracking at the beginning, but still the load's increasing. Then you get the shear band or the kink band forming, and then the kink band does work progressively. That controls the plateau. And then once you get a total load drop when you get toe rupture on the tensile side of the specimen. So it's compression, tension, shear all in one specimen and one structure. Quite a challenge. Because each of these, right, if you model in isolation, there's lots of detail that you need to include to get the response correctly. So we had to now decide how are we going to develop a hierarchical model that is able to capture those events yet have the fidelity to make it enough to computationally be efficient. We put more and more detail you run out of gas in the sense that you can't really make the computational model run fast enough for you to get an answer in a decent amount of time. So our scale, it's a multi-scaling approach with a global local strategy which is depicted here for this problem, right? So we are in the process of understanding how we can do it for larger structures. So we looked at the outside, the region in which there's no failure. We call it basically homogenized layers or homogenized material. In the region where that's failing, we need the details of the microstructure. But now the question is, what is that region? Well, the size of that region is now an unknown in the problem. And how you find that is you have to run your model until the results converge and do not depend anymore on the size of that region. Because the size of that region in relation to the size of the structure and the region where you homogenize will actually influence your results. So the unknown is the region in which you have a discrete or a more refined scale, or where you do multi-scaling. So we have the model as broken down into different constituents, but more details in this mesoscale model that I'll talk about. And then within that, there is yet another model at a lower subscale to model the toes that have the fibers and the matrix in it. All right, so now let's look at the matrix, the polymer itself. For that, there is two models, right? So the first part is a continuum damage theory formulation, right? Because it's micro-cracking, can't model every crack for the matrix. And then you run into a sort of a peak, and the post-peak, you see a drop if you test the matrix by itself. And for that, we use something that was actually originally developed by the community, concrete community. It's a smeared crack approach, in which we have a decreasing stress with an increasing strain, right? And now the question is how you combine them within the same sort of finite element framework. So we assumed it's a damaging material, so the instantaneous properties are the secant moduli and the shear moduli, and the Poisson's ratio, which we can get by knowing the equivalent stress and the equivalent strain for the material itself. And then we decompose the strain into two parts, the continuum strain and what we call a crack strain, right? And the crack strain is the strain that acts in the softening region, and the area under the traction separation law, which corresponds to the crack opening displacement, is your fracture toughness or your toughness. It's not really fracture, it's toughness because there's also damage in that region. And then when you want to embed this into a finite element scheme, you have to develop a method by which you work out the constitutive model for the matrix, which now with that additive decomposition of strain and making sure that you know which plane the crack forms in with the strain transformations, you get that box at the bottom, which now includes the continuum part and the crack part. Now for the crack part, you have what is known as the traction law. It's a diagonal law because the modes are separated, that's how you write. But then growth is mixed mode, which means you need to have a way to combine when you have mode 1, mode 2, etc. Now in the pure matrix, it's mode 1 because it's a pure isotropic polymer. So the cracks will want to grow in a direction where the maximum principal tensile stress is max and the crack forms perpendicular to that. But at an interface, it does not have to be that, because at the interface, the direction is fixed, but the growth is a mixed mode law. All right, now why is this important? What I'm saying is that if you don't have the length scales that are the area that is fitting inside one element, which is drawn schematically there, your calculations will be mesh dependent. So when you change the mesh, you'll get. So inputs to this model are material properties, but what the finite element code uses inside are not material properties, right? They are a function of the formulation and the material properties. That's how you recover mesh objectivity. Similar thing occurs also in a crack band model that is also used for softening. And there are other models as well. There are gradient models, etc. And I think I learned that one of the pioneers of those gradient models, hierarchical theories, was in this department. Fortunately, passed away, Professor Vardulakis. He has done a lot of work in shear banding in soils, for example. All right, so for the toe, we used a representation of what we call the concentric cylinder model, which is a representation of a toe. And the nice thing about this is that instead of just using the toe to get the properties, what we do is we solve, given the state of strain outside a concentric cylinder, we solve for the state of strain inside the cylinder, in the matrix and in the fiber. And then we used a secant approach to upgrade the stiffness of the matrix, and the fiber remains elastic throughout, but the matrix changes based on its equivalent stress law. And then we used a multi-scaling there, where at each integration point, this cylinder is situated in the toe. So you calculate that. But the advantage is that is not done numerically, it's done analytically. So the subscale calculations are analytical closed form in a secant sense. So the cylinder model is shown here. And the new thing here is that this model has been used in the composites literature for a while. What's new is that instead of just using it to find instantaneous properties, we actually solve for the strain and stress fields inside the cylinder. So given the state of strain outside the cylinder, which is coming from your macroscopic calculation, we solve for the states of strain and stress inside the cylinder, right? And so we checked it against our model, against a full 3D finite element model for that. And you can see that the contours match very well, and we get very, very good agreement, the analytical approach we are taking in a closed form sense. It's a MATLAB based, once those equations are, it's a MATLAB, but then it communicates with the main solver. In this case, we used Abacus to do the computations. So the chart is shown here. So we had to use a material subroutine. When we enter, we update the strains, compute the strains in the matrix from the model that I just described, compute the instantaneous matrix properties. From that, we compute the composite properties, and now this is for the toe. And then we pass that to update the stress, and we exit the user material subroutine. How do you evolve the toe nonlinear properties? Again, in the morning, I had a great conversation, very short but great conversation. Triaxiality, right? The toes inside are not under uniaxial stress, they are under triaxial stress states, right? Here in this department, there's a great lab that can do work where you can not only change the triaxiality, but you can control how much different directions you can put on material. So that's a great resource for getting data of the type that we need for this. So here we have two quantities, V1 and V2. These are basically the von Mises equivalent strain expressions. But what we found was that the mean controls how the equivalent stress and equivalent strain evolves, while the max actually controls the details of the shear evolution. It's a very interesting observation. Why? We are still trying to understand why when we do the experiments, but it turns out that that's what it is. So when we do that for a, say, hex pack unit cell, we use our model and a full 3D model. You can see that the nonlinear response is captured very well. The difference is the full 3D finite element model, if I did it finite element within a finite element multi-scaling, it would have taken forever. But now the subscale calculation is done analytically. So it speeds up your calculations very much. Still multi-scaling. shear banding, right? So Diane Yoon developed based on that multi-scale scheme I said, she developed a method by which you can see not only is the shear banding mesh objective, but it's a multi-scale, it's homogenized. So there's no fiber and matrix in this simulation, right? So it's a homogenized toe, right? But with the scheme where we, at each integration point, we bring in the fiber and the matrix properties, and we run it. You can see that as we refine the mesh, the details of the band width, the angle of the band are preserved. So this is very advantageous for these calculations. We don't have to do the microstructural detail meshing. You can see that the calculations are mesh objective. This is done in an explicit code. If it was done implicitly, using, let's say, a RIX or arc length solver, you know what the curve's going to look like. It's going to snap back. It's going to come back because those are negative, unstable equilibrium paths. But the important thing is to get the peak and the plateau loads correctly, which this calculation is able to do. So now these are anisotropic, the toes are anisotropic, so you have to look at the directions separately, compression and tension, as well as transverse direction failure, and in that case you can have also mixed mode evolution, as I pointed out earlier, because the fibers are constraining the crack to occur between certain layers. Now here I learned something interesting today in the morning, which I will be working on after I get a paper. In the compression, transverse compression direction, I learned that there is a modification which is much better to the classical Moe-Coulomb, and that's the Paul-Moe-Coulomb that rock mechanicians use. So I was very thrilled to learn about that, because there was some nice data shown which we would like to incorporate in a model like this. This in compression uses a classical Moe-Coulomb construction, which can be improved certainly with the data that I learned in the morning today. All right, so the smeared crack approach for the toe is very much like the matrix, except the directions are now different. So different directions you have to keep track of, because the toes are undulating. You need your local coordinate system to keep track of where things are. Now, furthermore, another important point. When the toes are constrained with surrounding material, you saw that the kinking is progressive, right? A kink band forms, right? And then loads transmitted and another kink band forms. Where you cannot capture that if you drive the traction law to zero, like on the tension side. So when something fails in tension, after complete failure, there's no tractions transmitted because there's nothing. But in compression, when you get a shear band, the tractions are still transmitted. So the confinement plateaus out the post-peak strength which we get from the micromechanics computations, right? So the stress drops, right? You saw that unstable drop, energy is dissipated, but then you get a plateau. Now if you don't use that, initially we were not, we couldn't capture the progressive failure. So in compression, there's nothing called really a toughness. If it's confined, the toughness keeps growing because there's progressive failure in the toe. So that's so you have residual strength carrying capability of the toe because of confinement. Here are the details of the model that we did. A typical model would be like this: the elastic properties plus all those. We used Abacus implicit and explicit. You'll see calculations. We make sure that our implicit and explicit codes agree, of course, because there's no guarantee on the explicit side. So I want to show some results of some of the experiments and the FEA explicit and the FEA implicit. These are the properties that we measured, some, and we have some from the manufacturer. So I want to show some results that we got. Our results are able to capture the progressive kinking that occurs on the top side when we put glass on the top and carbon at the bottom. you can see those red marks are those kink bands that form on the homogenized scale. And these are the results we get there in the FEA explicit and the implicit. It's not bad. It could be improved. There are improvements that we are thinking about, adding more features. So I want to remove the measures to show you what happens as we progress. You can see a first kink band forms just like in the experiment on the compression side first, and then you see the kinks multiplicating, right? More and more kinking occurs as load increases. There's no abrupt failure. The load keeps increasing still, right? Until there is sufficient kinking and the bottom side starts to fail in tension, where the toes rupture on the tension side. These are the toes only. Now, while this is going on, I removed the matrix. The matrix is cracking at the bottom, the matrix elements. I removed it to show, because the toes actually, the toes control the global collapse, but the progression of failure in the toes is controlled by the matrix. So it's a progressive failure with interaction between the constituents. What Dianyun says as FE original and FE smooth are the filtrations she did when she did the dynamic experiments. And you can see that when we change the glass on top and the carbon on top, you can see that the histories change, and you can see different behaviors. It's more dramatic in the next chart here, where glass is on the top, carbon on the bottom, and on the right-hand side, carbon on the top and glass in the bottom. You get progressive kinking much higher in the carbon on the top glass specimens, glass on the bottom specimens compared to the reverse. A larger energy absorption or energy dissipation. Final failure when you have tensile rupture of the toes. Carbon tensile rupture occurs much easier, glass not as easy. So the bottom line, you can design the architecture, right? This model, the elements of the model is showing that it can capture the events of the experiments we conducted, which provides us confidence now to start messing around with the architecture to see if I change different layers and different architectures, how I control my overall stiffness and the progression of failure. Now, impact loading is something that we are doing right now. So I want to change gears a little bit here. We use the same model for tensile loading of a different architecture, slightly different. Again, we have the same different scales, but here we did something slightly different. We used a software called Simpleware. It's a company that allows us to take very high-resolution micro-CT images of the entire coupon. So I first discovered it in the dental school at Michigan. Then I went to Washington and I found that the medical school there also has, they are using rat models to develop certain tissue growth mechanism studies. So they can take a rat and they can anesthetize it and get a resolution of the entire rat to within microns. And so when I came to Washington, the civil engineering department owns a very large, it's a SkyScan CT machine, which I'll show in the next slide, which has the ability to, sorry, in the slide after that. So the modeling was similar, but this time I modeled the entire coupon in the B area using this SkyScan image processing tool. What it does is it images the entire specimen, and then it writes an interface from which you can generate a finite element model, very detailed finite element model, right? So that's the details of the machine that we used. So civil engineering, why they did that is they have large specimens like some I saw here, where they want highly detailed microstructural information to look at progressive failure in concrete specimens where they are changing the mixtures, the particulates they add, the fibers they add, etc. Right? And so they want to do more refined models to understand how those models can be improved. So we used that machine, and we were able to get very, very high resolution images of these composites. Now, we are not able to get individual fibers, but we are close. We're getting to within 9 microns pixel sizes, while still imaging a fairly large object. So that's very, very appealing to me. And I am told that the company is now developing even a larger or a much more higher resolution machine. These are expensive. We were lucky. Civil engineering at Washington, we wrote an NSF major research equipment grant. And the machine cost $750,000. I'm told the next one is of the same order, a little bit more expensive. We can do things like this. We can get measures, segment it. We have to do a little bit of manipulating after the simple wear is done. But the whole specimen was imaged, and just wanted to see how it will do, and with the modeling strategies we adopted. And now here we use symmetry for the model, so the model scan, otherwise we lose resolution. So we scanned half the coupon, then we flipped it, mirror imaged about the top. So the coupons model symmetrically, right? But the properties are slightly perturbed so that one side has slightly different properties than the other. Because we wanted to, we know that in the real specimen, if we were able to take measurements of the properties, we know that they won't be exact, they'll be more random, right? So we did put very slight, 1%, so that if at all it fails in one side, just like we see in the experiment. And so that's what we get with a very large model. Now, what I'm showing here are what we actually see in tension. The coupon, this coupon fails like that, and that's that black curve there. And then after that, the load drops, right? So we did RVE studies. We took representative volume elements, and we did a perfect RVE, an imperfect RVE that was scanned and constructed more accurately. And then we did a 9 RVE, because remember, in damage and failure, the notion of an RVE is not just the geometric representative volume element, right? It's the physics representative volume element. Is your volume element able to capture the mechanisms that you want to capture, right? If you do it just based on geometry, you'll miss the boat, because that's just a geometrical representation. Physics, especially when there's localization, you need to have a correct number of RVs to capture that mechanics. So that's the middle 3. The coupon, the entire coupon simulation is that other red curve. You can see it does a fairly good job of capturing what we saw in the tensile test. Those are the toes that I isolated to show how the failure occurs in the toes. So just the front side, back side. The red now is the matrix cracking. The matrix that cracks, I'm showing the whole thing. And earlier I showed just the toes with the matrix removed, matrix elements removed for visualization purposes. And here I just show how the progression occurs, and it's actually quite remarkable. It's not exact, obviously, because specimen is not exact, but it has the features that we actually see in an experiment as well with DIC. We see the matrix cracking, and then we see that rupture event. We've done lots of tests with this material as well. So what have I really described here is that depending on the scale and depending on what you want to get, mechanics can be used carefully with details at different scales appropriately chosen to provide a computational framework that can be used for these types of composites. Now, I showed what I would call a direct numerical simulation, the large one, where you can take an image, convert that to a mesh, do the entire microstructure, and those results are in fairly good agreement with a macroscopic response predicted from in agreement with an experiment. Shows the progression and failure as well. And so the advantage of this is it allows fairly sophisticated calculations to be done ahead of time. If you did this with tests, for the system I showed you, it will take a long time. and it'll be very trial and error based because you're combining different materials. That's exactly what, by the way, the Boeing 787, the Boeing company learned as well when they built the 787 as an all-composite aircraft. They realized the sort of the Edisonian test everything and get data, it's not going to work. So this idea of using a computational framework to do modeling is also now pervasive in the aerospace community, and NASA has come out with what is known as the NASA 2040 vision. It's a great document. I know this is maybe a civil engineering audience, but they should read it because there's lots of mechanics in that document. Mechanics to influence how airplanes are designed, where simulation and tests are brought together in the certification of a plane that carries passengers. So for young people here, it's a great time to be in the field in mechanics because I think you'll see more and more computational developments with richness in the scales that we can model coming into the picture. So it's a great time to actually be in mechanics. So I offer my concluding remarks of what we did today or what I presented. But obviously there's more to be done. And just by talking to two people in your department in the morning, I learned quite a bit that I can just do for these models here itself. So really pleased to be here, and I want to thank you for listening. Thank you.
Okay, we'll open floor for questions. Any question?
Yes.
I'm thinking back to your opening remarks where you're talking about strain rate dependence. I'm
Right.
curious, in woven materials,
Right.
is the strain rate dependent because of a property of the weave or a property of the material that goes into the yarn?
So the dependence, the strain, it's a mixture of both, Randall. So what happens is that the polymer is rate dependent, right? And the polymer is in the yarns, but it's also dispersed everywhere, right? So the way we model it, we model the yarns separately as a entity, one homogenized entity. So if you do, say, Hopkinson bar tests on the toes, you can see the strain rate dependency, but it comes from the yarn, from the matrix, but it also comes from the interface. Now, chemists have been very good at developing what they call sizing. So if you tell them ahead of time that you're using a particular polymer with a particular fiber, they prepare the surface of the fiber such that the failure occurs in the matrix, not at the interface. Now, 15 years ago, that was not the case. You could remove the fiber completely out. Now, the bonding is covalent bonding on the surface so strong that the polymer, because it's networks, it fails, but it's close to the, so the rate dependency comes from the polymer. So ideally, you should be able to do this whole thing just by knowing only the polymer properties and the fiber properties. We are not to that level yet because we'll have to upscale it. We have to go to different scales. But that's where it comes from, yes. Yeah.
Okay, any more questions?
So you might have mentioned this, but at the beginning you talked about the fact that when you have fibers and matrix, so you might have this interface region in between that is neither fiber nor matrix anymore, right? Has intermediate properties. Is that accounted for in any regions of your matrix?
No. The answer is no, but this is a great question. So I just came back here from US CAR, right? US CAR is a consortium of universities that are and companies working to develop low-cost composites for automobile applications, right? Now, there was a gentleman talking about tailoring the interface by using nanoparticles. And what they showed is that by tailoring the interface with between the fiber and the matrix, by doing that, you can extend the shear stress response I showed you earlier to a much larger, much longer region. You can increase the ductility, so to speak, by doing that. We haven't, in these materials, we haven't done that. But your question is timely because people are doing that. And what they're finding is then you get even more work out of getting the matrix away from the interface to fail more and more. So you want progressive failure, right? You want to increase that curve. You want to have more ductility. And that can actually help.
Yeah, I've heard something like that in the context of tire rubber compound, also with nanoparticles to achieve what you're saying.
That's right. It's possible. But this is at the nanoscale now. They're putting nanoparticles, nanometer level particles between the fiber and the fibers are 6 microns in diameter. So these are nano. So and they're developing techniques to do that. I think that will be fantastic. Yeah.
Maybe one last question. Maybe I'll do a short question.
Sure.
When you have this graph on the stress and the separation curve on the tension side, the compression side,
Yes.
and you have this notion H.
Yes.
This H has a physical meaning of maybe the bandwidth. I just wonder the bandwidth in the tension side, the compression side, should it be the same or they should be different?
That's a great question. They should be different. And I think in our model, we have not considered those differences.
Okay, I see.
That's a good question, yes.
Okay.
To preserve mesh objectivity.
Yes,
It's
okay.
not, because the H will be different depending on how you scale the toughnesses.
Right.
That's correct.
Okay,
Yeah.
thanks. Okay, with that, let's thank our speaker again.